This is the Pharmacia LKB ECPS 3000/150. What it is a high voltage power supply for medical use. Had this kicking around in the workshop for a while. I've got another unit I use occasionally, which is a 300, well, it was a 200 volts at 400 milliamps. I managed to get 300 volts out of it. But this is one that's been kicking around for a while in the workshop. When I first plugged it in, I connected it up to my Fluke DVM. It's Fluke here, actually it's another model, but same model Fluke as that, or same style Fluke as that, should I say. And I switched it on and set it to 500 volts, and it blew the Fluke up. Took the MOV out on the front end. So I was a bit disappointed at that, so I sort of repaired the Fluke meter, and I thought, well, I'll have a look at this some other time, see what's going wrong with it. So today is the day I've been looking at it. The problem with the unit, it had two problems that makes it more or less unusable on the bench for anything other than maybe in the pharmacy market, and I don't even know if this one's got a fault. I'm not sure it's supposed to do this. There's no information at all on these. It's a highly dangerous piece of equipment, actually. It's something that produces 3 kV at 150 milliamps will fry you. You know, it's really nasty bit of kit in the wrong hands. What I'm trying to do is get away for two problems. The first problem is if I enable the power when it was a standard, I would get no output unless I reached about 400 or 500 volts, and then suddenly the power would turn on. So you could set your voltage up and enable the output with the enable switch there, the switch that's right at the bottom, the little toggle switch, and I'd get no output at all. You'd wind the volts up on the pots up here, and then suddenly the output would burst into life. So that was useless. That was no good. You couldn't sort of wind anything up slowly because you wouldn't have any output unless you had some load on the output, or you know, or well, you had to have load on the output, or you just couldn't get an output out of the bit. So you couldn't get anything sensible at all. So that problem I've been looking at this morning. That's been my first problem, to try and work out why it does that. And it's very difficult without a manual, but I have tracked sort of circuits diagrams back, and I've come back to this circuit here, which looks like, let me just turn it off, I don't stick my hands in it. You see this resistor here that I've tacked on or bodged on. This looks like some form of over voltage protection circuit, because if I put a decade box across there, it will actually get to a certain voltage and just lock itself out. Now, I put a decade resistor across here, as you can see, and the other end of the resistor goes to a 12 volt reference. And when I do that, it enables the output. So it's something to do with the over voltage protection circuit. It's not working correctly, I don't think. So that's a 390k resistor connected to the 5 volt reference, and that resistor goes back up to a LM324 at the top there into one of its comparators, and that enables the output all the time. So that was the first fix. I managed to get over the problem with the no output if we've got no load on the unit. So now I can switch it on and actually get output from 10 volts all the way up. There but lies the second problem with the power supply, and probably the most dangerous, and the one that actually killed the Fluke in the first place. When you switch it on, you get a massive voltage overshoot, and I shall demonstrate this now. Now, what I'm going to do is I'm going to program the unit to a set voltage. Now, having to use this old Simpson meter. It's a nice old meter, actually. I've never really used it that much, but I've been using that because they'll put up with a transit of high voltage spike rather than the electronics ones that will all go into burn all the protection circuitry out. So I connected it up. I'm going to switch it back on, and we set our voltage here with the set button. So the set button's in, and we're going to program. A bit difficult to do this on the bench because I need access to both sides of it. Let's set it to something not too scary, like 300 volts. And when I enable the output, right, if I press the set button off now, it's showing you the actual voltage. Now, what I'll do is I'll switch it on with the enable switch. I'll show you what the Simpson does. Now, this is the big problem. If I enable it, so we're on the 1000 volt range, so we're expecting it to go about 1/3 of the way up the dial. So I'm going to enable the output. See that? CD 1 kV for a minute. Now it's settled down. So we're getting a massive surge in output. Now that's been a real problem to try and work out what it is. It's bad even at sort of, if you set it for program for 20 or 30 volts, it would jump up to 200-300 volts and then settle back down, which is unacceptable, and you can't use it on electronic gear really. It's just too difficult to control and predict what it's going to do. Now, as I say, we haven't had any luck with the circuit diagrams on this. There's no Pharmacia don't seem to have any informational service data on the net. It's obviously a sort of closed loop they run. So I've been looking through and following back feedback circuits. You can see here on the left hand side, this is the high voltage transformer. You've got the rectifier, the capacitors for storage, and the multipliers here, and then you've got a various number of dropper resistors that take the feedback back to the op amp to keep the thing in a closed loop situation. Now the problems notorious with high voltage power supplies, their loop response becomes slow because you're so far away from the main control source, so they're all a bit sort of sloppy. I've been searching around on the internet trying to find out how this thing works. This is the main switching transistor here. This seems to do all the switching for the switching transformer here. So this is basically, looks like the gate drive comes in from this gate drive transformer here to this switching transistor, which is I think it's a FET, but it might not be, and switches this transistor. So what happens is when you enable it, you get a large splodge of information, large sort of load of rubbish come through on the PWM. You get a large burst of signal. That's obviously goes into the transformer, charges the capacitors up, and it overshoots. By that time, the loop response has realised that oh my god, there's too many volts. Shut down. You can see it do it. You monitor the chip. You can see it shuts the pin right down, lets it discharge slowly. As the capacitor discharges and it gets sort of to unity, it starts to come back up again and stabilize, and you get outputs again. I can try and demonstrate what it does if I switch it on in this uncontrolled fashion. Not easy to do. I haven't got enough hands. Let me just try and set up. Trying to find somewhere where I can actually get a gate drive signal on the. Yeah, I can, just about there, I think. So, okay, so there's one of our gate drive signals, and you can see it there. So what I'm going to do is I'm going to try and do a single shot of that, of the startup procedure. So let's set the scope up to normal. Right, triggering on positive edge. Slope. Positive edge. Right, so I'm going to turn the and disable the output again. Puts off. So we're ready for a single sweep. Now I need to set the time base a bit slower. Might be a bit of jiggery pokery to get this to run. Right, I'm going to enable the output. Right, you can see that. You see the initial surge of pulses. Let me just slow the time base down even further. But I want to show you. Actually, I'll turn the grid off as well so you can see a bit clearer. There's the grid. Clear the cursors. So I've got nothing on the clear cursors. There we go. So we're going to start again. I'm going to start it up again. You'll see what happens. Let's trigger from the left hand side as well. So bear with me a minute. Trigger from the left. You're single. We're ready to go again. So what we're doing is we're looking for a burst of pulses from the PWM. Nothing as the comparator shuts down. On. I think we're just off the edge of the scale. There we go, and it's starting to come into regulation now. You see there's a couple of heartbeat pulses. It's just topping the capacitor up, but we're still missed the initial pulses. Let's bring this down a bit. This is a bit of fun trying to get these to trigger at the right points. Let's try again. Enable. I should be doing it so badly now because I've been messing around with stuff. Try a bit further. Turn it off again. What was happening is we're getting this burst of data on the left hand side, and then nothing, and then that's better, I think. If I've got enough, no, I haven't got enough data counts because I've triggered in the centre of the screen. I don't think it's going to have much luck showing you this. I'll try one more time. Okay, that's the actual thing running at the moment. That's it, as I say, just charging the capacitor up. Try again. Wait for it to discharge. I don't know why it's not getting the. Let me try and get the scope set up, and then I'll come back. Okay, I think that's the best I'm going to get. Focus again. That's the initial switch on. There's that pulse that charges the capacitor up, a big pulse. And then just have a look at the duty cycle on that and see what it looks like. So scroll through to that pulse. It's the trouble, I haven't got the memory depth really of this scope. It hasn't got a huge amount of memory. So there are initial pulses, yeah. So it fires those off. Straight away goes overshoots, loses, shuts the PWM down because the loop error amplifier shut that loop down, and then it starts to regulate after that point. If you increase that voltage, that takes even longer to settle back. So that's the initial problem. I need to get rid of this pulse, or these pulses here. If I can get rid of these pulses, these initial surging pulses, then we don't have the overshoot problem. Struggling and focusing at the moment. So what I've been doing was messing about with the chip inside, and the chip inside is a TDA 1060, and that's this chip up here, and it's basically sort of a PWM. It doesn't look quite like a PWM I'm used to, but that's what that chip is there, that Philips chip, as you can see there. Now the pin I've been messing around with is I suppose it's the error amplifier. I'm not entirely sure what it is, but I looked at the schematics, and it sort of suggests that if you put a capacitor across it and pull it down to ground, that affects the soft start. And when I did that, I got an even longer overshoot, and the voltage went off the scale. I lost, the loop was so slow that I couldn't actually get control of the unit. I had to shut it off because it was, the voltage was ramping up and up and up, getting dangerous. So what I've done is I've been experimenting with the Decade box, and the Decade box, this old Heathkit Decade box, I've been connecting across this pin, and that pin is up here, and to ground. Now I've been experimenting with different resistances, trying to see if I can get any change in output. I suppose I should turn it off when I've got my hands in there, so the thing's lethal. Now this is so this is controlling the hopefully the feedback from the PWM to try and stop it from doing that initial pulse and uncontrollable pulse. So let's switch it on and see what happens. There you go. Now it still overshoots, but it's far more controlled, and it comes up in a more controlled fashion. Let's turn it off again. You can actually adjust that down even further. Now you still get quite a few volts overshoot at the lower range, but certainly in the higher range it's a less of a percentage, if you like. So switch it on again. On. Much better. You can see it's still overshooting by probably 100 volts or so. So let's try and cramp that down a bit further. I'm just bringing this point closer to ground. And enabling. Up you go, go on. No, I've gone a little bit too far now, it's not quite going. So it's going to be probably a bit of a tricky pokery. Yeah, it's having a bit of trouble regulating there now. But are we at the we're at the set voltage, so I did program 320 volts, is producing that. Let's try it off again. So this seems to work quite well. This seems to actually control the overshoot more or less perfectly. It's a bit slow to come up. as you can see there, and you see it's metal wobbling about as it's finding sort of equilibrium. So I think if we put something like a 6K5, and this is a 5K6, that's a pretty standard resistor, I think that would be basically fix that problem, and that should actually make the thing a lot more safer to use for sort of like electronics. There must be a better way of doing this. One more time. Yeah, and it doesn't hesitate so much now. So that's with the resistor box on, and let's do it without again. So this is it disconnected. This is how it is a standard. Whoa! So, you know, huge difference, huge improvement. So I'm quite pleased with what I've achieved on this power supply this afternoon. I've actually got it to sort of like quite a usable and fairly safe operating sort of mode. So it's, you know, it's not going to do any damage to anything. It might be interesting to have a look at the PWM's output when it's running now, just to see how well what it should do is it should start up with some very narrow duty cycle and slowly increase the duty cycle as it needs more power to charge the capacitors up. That's how it works. It's not the amount of time the pulses are produced, it's the duty cycle and how much energy it puts into the actual transformer itself. In a shutdown voltage scenario, it will actually stop the pulses altogether. You know, that's a total shutdown, so it doesn't put any power or energy into the transformer at all. So let me just run it again and set the scope up so we can actually see what the duty cycle looks like. Get the scope triggering properly. Unfortunately, where I am at the moment on the unit, it's not the best place. I've got output, so I should be able to see something. Got a test point here somewhere. Let me just find this test point and I'll come back. Right, so let me just show you how it starts up now. So let's turn the output off. Okay, it's gone to normal triggering, so we clear the screen. And what we'll do is we'll start up. You should see initial pulse, and then it will become very narrow. So and then it should widen as it needs more volts. So let's switch it on. There's a pulse, and see it drops out suddenly as it sort of loses regulation, and then it sort of establishes itself. So let's turn the volts up, and you should see a sort of widen, sort of increase to give us a sharp turn on the volts. You can just about make that out again. See, now what happens when I drop the voltage back? The pulse width will narrow down. There you go. So it looks like it's working fine. Just widen the pulses right out. Just turning the volts down and turning it up. And likewise, if I put more load on it, that pulse width will become wider and wider. So if I put a heavy load across the output, that pulse width will become wider. So it looks like it's actually quite a good fix, and probably worth, if you're looking for a cheap power supply. These things are very cheap on eBay. I only paid about 30-40 quid for this. You look for a high voltage power supply, you're talking, well, thousands usually. Obviously, if you do work with one of these, with that Mr. Carlson's lab, he says it every time, you're doing it at your own risk. This sort of thing is much more dangerous than anything else I work on. You know, valve radios and things are sort of like a walk in the park. This is lethal, you know, really dangerous voltages and current as well. You know, 150 milliamps at 3 kV. You've got no chance of putting up with a shock like that. So you need to know what you're doing. But I hope this is of some interest, and thanks for watching.